Welcome to the third lecture for the course Introduction to Mobile Robotics. We are seeing the Module 1 for this course. Today we are going to see the constraints that is being faced for the locomotion principles and also the different motion control, the kinematics dealing with mobile robotics. Locomotion refers to the mechanisms that enable a mobile robot to move through its environment. A mobile robot can move in many different ways, such as walking, running, jumping, sliding, crawling, swimming, flying, and rolling. Most of these locomotion mechanisms are inspired by biological systems observed in nature. However, there is one important exception, which is actively powered wheel. The wheel is a human invention and is not commonly found in biological systems. Wheeled locomotion is extremely efficient on flat and hard surfaces, which is why it is widely used in vehicles and indoor mobile robots. On the other hand, biological locomotion systems perform better in rough, uneven, and unstructured environments. Therefore, the choice of locomotion mechanisms depends strongly on the operating environment. Now we will see the difference between the biological versus wheeled locomotion. Biological locomotion includes mechanisms such as crawling, sliding, running, jumping, and walking. Each of these mechanisms differ in terms of resistance to motion and the type of kinematics involved. Crawling and sliding are dominated by friction forces. Running and jumping involve oscillatory motion and loss of kinetic energy. Walking can be approximated as a rolling motion of a polygon, where each step represents one side of a polygon. In contrast, wheeled locomotion is mechanically simpler and more energy efficient on flat terrain. However, wheels perform poorly on soft or uneven surfaces because of the rolling friction increase. Hence, biological locomotion provides better adaptability while wheeled locomotion provides better efficiency. Now we'll see how it is efficiently working in terrain considerations. The efficiency of locomotion mechanisms depends strongly on terrain properties such as flatness and hardness. Wheeled locomotion achieves very high efficiency on smooth, hard surfaces like roads or railway tracks. This is clearly seen in the comparison of specific power versus speed, where wheel systems require less power for higher speeds. Leg locomotion, although less energy efficient, offers superior adaptability and maneuverability on rough terrain. This makes leg robots suitable for outdoor and unstructured environments. To overcome the limitations of both approaches, hybrid locomotion systems such as wheel leg robots are used. These systems combine efficiency of wheels with adaptability of legs, making them suitably for rough terrain navigation. Now we'll see the key issues in locomotion. First, we'll consider the case of stability. There are several key issues that must be considered while designing a locomotion system. The first major issue is stability. Stability depends on the number and geometry of contact points, the position of the center of gravity, whether the robot is statically or dynamically stable, and the inclination of the terrain. The second issue is the characteristics of contact. This includes the size and shape of the contact point or path, the angle of contact between the robot and the ground, and the friction between them. The third issue is a type of environment. The structure of the terrain and the medium, such as air, water, soft ground, or hard ground, significantly affect the choice of locomotion mechanism. Now we'll see the kinematic modeling of mobile robots. Kinematics deals with the geometric description of motion without considering forces or masses. In mobile robotics, kinematic modeling is essential for control, navigation, and motion planning. A mobile robot is modeled as a rigid body moving on a plane with 3 degrees of freedom: position along the x axis, position along the y axis, and orientation represented by the angle theta. To describe motion, two different frames are defined: the global or inertial reference frame and the robot or local reference frame. The robot's pose is expressed using a state vector consisting of x, y, and theta. This representation allows us to mathematically describe the robot's motion. Now we'll see the forward kinematics of mobile robots. Forward kinematics determines how the robot moves when the wheel speeds are given. In other words, it computes the linear and angular velocity of the robots based on wheel rotation. Motion initially described in the robot's local reference frame is transferred into global reference frame using a rotation matrix that depends on the robot's orientation angle theta. For a differential drive robot, each wheel contributes independently to the robot's motion. If both wheels rotate at the same speed, the robot moves in a straight line. If the wheel speeds are different, the robot follows a curved path. Thus, forward kinematics connects wheel motion to overall robot motion. Next is the wheel kinematic constraints. Wheel kinematics impose constraints on robot motion due to the rolling contact with the ground. There are two fundamental constraints that apply to wheels. The first is the rolling constraint, which states that the wheel must roll without slipping in the direction of motion. The second is the sliding constraint, which states that the wheel must not slip sideways. Based on these constraints, the wheels are classified into fixed standard wheels, steerable standard wheels, caster wheels, Swedish or omnidirectional wheels, and spherical wheels. Each wheel type imposes different constraints which directly affect the robot's mobility and maneuverability. Finally, we are going to see the motion control based on kinematics. Motion control uses kinematic models to generate appropriate wheel commands so that the robot follows a desired path or trajectory. The kinematic constraints imposed by all the wheels are combined to determine the overall motion constraints of the robot. Robots with standard wheels are generally non-holonomic, meaning they cannot move freely in all directions. In contrast, robots with Swedish or spherical wheels can achieve omnidirectional motion. Thus, kinematic modeling plays a crucial role in path tracking, trajectory generation, and analyzing the maneuverability of mobile robots.